Welcome friends, welcome back to the hangar. Well, actually we're out on the ramp at Edenvale and Mike Victor uniform is finished. All of the wing work that we were doing is done, but I still have episodes to show you the wing work being done, the stuff being put on. But I realized that, I'm so involved with this project, I didn't explain what we were doing well enough, especially for those people that aren't aviation geeks. Who were wondering why we were playing around with the wings, what we were doing to the wings, and how that's going to affect flight. So I thought I'd give everyone an overview of what happened. It is super windy out here today. That windsock is straight out. So we've got a 15-knot wind here at Edenvale today. So here we go. Here's what's happened. In the last episode, what you saw was a new leading edge put on the wing. This is called a STOL cuff. And here's why I put that on. This aircraft was built in 1961. It's a 1961 model year 172B. It was actually constructed in September and October of 1960. A lot has happened in the world of aeronautical design in the ensuing years. And there's also every design decision is a compromise. And for aircraft, it's no different. So you have to look at, in that time period, maybe they hadn't come up with a leading edge design that was great yet, perfect yet, or better yet. Or maybe they had a great leading edge design, but it was too expensive to put on the aircraft, and the production time, production costs, so on and so forth. The end cost of the airplane was going to be too expensive. So you compromise and they changed the leading edge. And the leading edge was fine. These aircraft are out there flying today, and they fly perfectly well. But in the ensuing years, Cessna on the 172 has changed the leading edge. And other companies have come along and said, for these earlier aircraft, we can give you a leading edge that gives you better slow speed capabilities. And that's really what I'm looking for. You want to change the stall speed of the wing. And what I mean by stall speed is you get an angle of attack. So as the wing's going through the air, it goes through the air. But as you slow down, you have to raise the front part of the wing, angle of attack, in order to keep the wing flying through the air without losing altitude. And as you raise that angle of attack, the air gets turbulent and it breaks away from the top side of the wing. How do I explain this? Because I'm not an aeronautical engineer, so I have a basic understanding of what's happening here, but maybe my explanation isn't going to be good enough. But essentially what this new leading edge does is, I showed you in the shop when we put it on, it sort of comes out and it drops down. And so that little bit of droop changes the way that the air flows over the top of the wing. That lowers your stall speed, which means you can fly slower. You can fly slower, which allows you to land slower, or land at the same speed but have a bigger margin of error. And I think that's important, that margin of error. Because landing and taking off, you're at slow speeds, you're low to the ground. That's when you don't want to have any problems. So this is to mitigate that. We also put on these little fins, and they go along the leading edge of the wing, and they're at an angle, they angle in to the wind. Those are called vortex generators, and they do what the label says. They generate vortexes or vortices. And when you get that wing into a really high angle of attack, and the airflow starts to break away, and it doesn't follow the wing the way it's supposed to, these VGs, vortex generators, the air hits here, and because it's on an angle, it forces the air over this way, and then in the air spins. And as it spins along the top of the wing, it conforms and it sticks better to the top of the wing, which keeps the wing from stalling. Am I explaining this correctly? It's something that if you wanted to read aeronautical engineering papers, you could spend the rest of your life reading these papers and figuring out how it works. But again, it keeps the wing from stalling at slow speed, allows you to come in slower, and if you come in to land slower, you have less energy. Less energy means that you can land in a shorter distance. Less energy means that you're not putting as much stress on the airplane when you touch down. Less energy means all of those things, as well as you can still bring it in at 65 miles an hour, which is the speed that you're supposed to land this at. Still bring it in at 65 miles an hour and give you a margin of error that is much wider, that if anything happens on final approach, you're not going to stall and then stall spin, which usually ends up fatal. Trying not to end up fatal. The final piece of the puzzle is this wing extension. So the wing used to end here, and it now comes out to here. So we've added 18 inches of wing to each side of this aircraft. That increase of wing area increases your lift. So that really helps me on takeoff. Now I can get the wing into the air flying at a lower speed. So instead of rotating at 60 or 65 miles an hour, I can now rotate at 40 miles an hour. We can get into the air at a lower speed off the runway, shorter takeoff, and the added lift means that I can climb faster to get over obstacles, get to altitude faster. Also on landing, again, this lowers my stall speed, brings it down to the point, higher margin of error, slower speeds on landing, less stress on the airframe, shorter landing period. Now, I've been flying this airplane now for about 20 hours since we did the work in the shop. So you're going to see the work coming up in the next episode. I've been flying this plane now 20 hours, and I have to tell you, it is scary slow in the stall. I mean, it is so slow, and you come in so slow. It's beyond my capabilities at this point. But I'll get there. I will get there. Now, on the tail of my fixture uniform, we also put Vortex generators on the vertical stabilizer and on the horizontal stabilizer underneath. The VGs do a couple of other things as well. That the vortices that they generate at slower speeds, all of your ailerons and elevators and rudder aren't as effective because there's not as much air flowing over them, and it's not as tight and conformed and clean, and so you start to lose authority. And what that means is that you can't steer as well. Perfectly fine layman's terms, you can't steer as well. Putting the Vortex generators on the other surfaces means that there is more air flowing across them, or the air that's flowing across them is flowing across them in a way that gives them authority. So at slower speeds, you can still steer this aircraft, which is a problem. If you get too slow and you can't steer, well then what's the point of going slow if you can't control it? This improves control. And one of the other things that we did while putting on the wing extensions is you have to strengthen the wing. We're adding a lot of new loading to the wing, a lot of extra pressure. And so part of the WingX extensions is strengthening the wing. And so you can just barely see it here. That's a new strap that we've put in between the skin and the spar. There's quite a bit of that going on. There's another one on the top edge that we've strengthened the wing. And also back here, you're probably not going to be able to see it. You'll see it when we actually do it. But there's another strengthening strap along the rear spar by the fuel tank. And what those straps are doing is strengthening the overall wing, allowing it to take more load and more forces. Now this is a 172B from 1961. If you've got a 172 that was built in, say, I don't know, 1975 or 1980, you don't need some of that strengthening because Cessna already added it. As they moved along with production, they changed the designs of the plane a little bit. And so your aircraft may have those straps. We had to put them in. One last addition is this hook-looking thing. It is a skid plate. Plain and simple, a skid plate. This aircraft now takes off in such a short manner that the tail will drag on the runway, which is not good. So this protects the tail, takes up some of the shock and rubs along the runway and keeps everything safe. I hope this all makes sense. I am really happy with it. So far, it is working out really well. I like the slow speed, although I'm a little bit scared by it and I haven't quite gotten used to it yet. There is no change in top speed. The aircraft still flies at the same top speed. There is no increase in fuel use. It still cruises at a really nice fuel flow rate, the same as it did before. So there hasn't been any adverse effect. I'm sure there is an adverse effect. I just haven't found it yet. I really haven't found it yet. So I hope you come back for the next episode where Andre is putting the WingX wing extensions on. A little bit geeky, but I think it's kind of interesting if you have an aircraft and you're thinking about this sort of modification. And then we're going to start flying. Mike Victor uniform. I'm going to start bringing you along. Julie and I are going to go out and start doing some traveling. So thanks for stopping by. See you again soon. So what we're looking at is the air flows over the top of the wing, and your center of lift is, let's just say it's somewhere here. And as the angle of attack changes, that center of lift moves forward or back, depending on what your angle is. And if your angle moves too far forward or too far back, the wing stops working, it stalls. You lose all lift. And so the air comes over the top and it conforms along here like this. Flows over. But as you slow down and your angle of attack increases, the air comes over the top and then it breaks away. And as it breaks away, that's when the wing starts to lose lift. And once it completely breaks away, it loses all lift, and your ailerons and flaps aren't as effective. So what this new profile on the front of the wing does is it makes sure that as you increase your angle of attack and your speed slows, air flows and conforms to the top of the wing skin for a longer period of time before it breaks away. That's where we come to these vortex generators again. So the air hits these and they're on an angle. So the air hits this and then comes over and spins. And as that air is spinning along like that, it sticks. I know sticks is not the right word, and if you're an aeronautical engineer, you're probably cringing by me saying that the air sticks to the top of the wing. But from a layman's point of view, essentially that's what's happening. The air is sticking to the top of the wing. So these two things help that. The wing extension adds lift, adds wing area. We've got 18 inches of new wing on each side. That extra area adds lift, which helps with slow speed and for takeoff and climbing.